This is a summary of calculus concepts and applied approach to mathematics of change 4th edition, lesson 4.1, approximating change. So let's begin. So in your discussion of linear models, that the slope of the line is y is equal to ax plus b, this is just y is equal to mx plus b. So we know this is slope. So basically it says as y changes when x changes by 1 unit. So let's look at an example. The amount spent on pollution control in the United States during the 1980s can be described by this equation. So this is the amount it changes, and this is in billions of dollars. So 3.79 billions of dollars per year, and T is since 1990. So we can say that each year during the 1980s, an additional $3.79 billion was spent on pollution. Why did I say population? It follows that every 2 years. So because we know this is the rate of change, so $3.79 billion per year. If you want to figure out how much spending will increase in 2 years, you'll just multiply it 2. And if you want to figure out how much you'll increase every 3 years, you'll just multiply it by 3. And that will give you how much it will change, the spending. So the problem with this is that the rate of change, these slopes, is only an approximation, because the slope of the function may not be the same. So if you find the point of tangency here, if you find the derivative here, let's say your derivative has a slope of 1, okay, that's good. But if you go here, the slope is drastically different. So what this whole thing is saying over here and over here is that the further you move away from the point of tangency, the less likely the derivative is going to be an accurate representation of the rate of change. So let me repeat this. You have a function like this. Okay? Let's say you have a point here. The instantaneous rate of change here, so the derivative, let's see, has a slope of, let's say this, 3.79. But the further you move away from a point, so let's say you use this line to estimate the rate of change of this year, the less likely it will be accurate. So the less likely it will be different in actuality. That's all it is saying. Okay, this is basically what I just said. So take a moment to read this. So, during the 1990s, a pound of salted grade AA butter can be modeled by this equation. So, this is the average price of butter. So you plug the year in from the 1990s, right? So let's say it's 1992 and you want to find the price of butter. You would plug 2 in, blah, 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 do your calculations, and you will find the average price of butter. Awesome. Now you want to find the derivative. By the way, all this means dp over dt is the derivative. This is just equal to p prime. Awesome. You did that, found your derivative. Awesome. Now it's asking you to find it at t is equal at 8 years. So find it in 1998. Awesome. You plug it in and you get 54 cents per year. So at 1998, the price of butter will rise 54 cents per year. But that is the instantaneous rate of change, remember. So that will be the rate of change at 1998. So what this paragraph is saying, that let's look at the let's go back and plug 8 into the actual equation. So you get this 296, and we estimated the following year, because it's 0.54 cents, it'll approximately add that to this, you get 350. And because of this, we can approximate how much it will increase half the year. So this is for 1 year. So half the year would be 1/2 0.54. So let's look at figure 4.1. What this shows is PT, the average price of butter, and the tangent line. The tangent line is what you calculated over here. So let's see. So this is where you calculated it at 8, right? So this is the concept I was talking about. The further you deviate away from the original point that you calculated, the less likely the tangent line will be accurate. That's all it is saying. And in this chart over here, that's all it is saying. So as we can say, so this is 1/4. So this is 3 months from the end of 1998. You calculate the price from the equation. So 8.25 years since 1990. Get 310. Now let's use the approximated price or the derivative to calculate. It doesn't deviate, but the further time goes away, the more it's going to deviate because it's less accurate. Because remember, the derivative is the instantaneous rate of change. Okay. So all this is saying over here is that the shorter the time period, so the shorter the time period, the closer the approximated price is to the given model. And the given model is the derivative. So if you calculated it for 1990, plug it in for 1991 and 1993. Which one is it going to be closer to the actuality? Obviously 1991, because that's closer to the given model. Okay, so all this is saying, forget this. Let's look over here. So all this is saying is approximating rate of change. So when you want to find the rate of change, what would you do in Algebra 1? You would do rise over run. So that's just the change of y over the change of x. So let's look over here. So let's say you calculated the derivative for this, right? So that's f of x. And this is f of x. So just say pretend this is 8, okay? All this is saying is 8 plus 1. Let's pretend h is 1. And this is x. And let's say x is just 3. So this is just going to be 3 plus 1. So how do you calculate the rate of change? Oh my god, it's the slope of the tangent line. You can take a deeper look, but all it is saying is that the rate of change is the tangent line in more fancier terms. Okay. So this is just broken up. So let's look at this. So all this is saying is that f of x minus f of x plus h minus f of x is approximately the change of x, f prime, to respects of h. And h would be like the time value, like the thing you plug into the derivative. So let's just make sure we did everything here. Yeah, awesome. You don't really need to, just make sure you understand this conceptually. And this is just solved for a different thing. So this is approximating the result of the change. So rather than approximating what the change, what will happen, like what will happen marginally, what would be an addition, this this is what would happen, like the actual number, right? This would be the result of the change. So this would be like the output of, yeah. Okay, just ignore this. This isn't important. Let's look at this problem, okay? I'm going to delete this. These are my notes. So let's look at this problem. We'll do this together. So the temperature for 2-hour period after thunderstorm can be modeled by this. So this is the model, okay? Let's do this. So 2 hours, we know, is 120 minutes. This is always good to do. Okay. Use the rate of change. Okay, so what does that mean? Use the rate of change of TH. Rate of change of ding, 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 derivative. Awesome. Find the derivative. Okay, let's scroll down. That's your derivative. Then it says how much, and then find it at 0.25. So what's 0.25 of 2 hours? That's literally just going to be, let's do 0.25 times 120. That's 30 minutes. Okay, this is just good notes to always do. Then we evaluate the equation for 0.25. So you plug 0.25 into the derivative, right? And then you get this. So that's the rate of change instantaneously. So that's the slope, the slope at 30 minutes after the storm. So that's how much it's going to change exactly at 30 minutes after the storm. But we don't know if it's going to continue to change at this rate. We don't know if the temperature is going to continuously drop 6.34 degrees Fahrenheit per hour. So then let's go down. So how would you find the change of temperature between 15 and 20 minutes after the storm? So what does it say here? The question says, estimate by how much the temperature changed between 15 and 20 minutes after the storm. So what do? This is what you do. So you have, this is your rate, right? So you're going to have your rate that you found, the slope, at this point, times 20 minus 15 all over, because of course it's in hours, we're just going to do 60. So the rate times 5 over 60, this simplifies to 1/12, because it's asking you the change between 15 and 20, so you have to subtract them, and the rate is negative 0.634 degrees Fahrenheit, and you multiply that by 1/12. That will be how much it, and you're estimating. Keep in mind, you're estimating. So then you get that answer. Awesome. Now let's look at the second question. Find the temperature and the rate of change at, okay, same thing. We're going to do the same thing. Plug 1.5 in, the temperature, into the original. Then plug 1.5 in to the derivative. So let's see. Plug 1.5 in, we get this. Then plug it into the derivative. And the temperature is going to go up 13.5 degrees Fahrenheit per hour. So this is the slope. The instantaneous rate of change 1.5 hours after the storm. Okay, now using only the answer to part B, so only this slope, to estimate the temperature between 1 hour and 40 minutes after the storm began. Okay, so how are we going to do this? To estimate the temperature of 1 hour, 40 minutes after the storm began. So we know 1.5, what is that? That's 1 hour and 30 minutes. So let's just keep that in mind. So that's a difference of 10 minutes. So how are you going to do that? Okay, the problem says note that 40 minutes is 2/3 of an hour. So 1 hour and 40 minutes is 1/3. Okay, so the temperature of 1 hour of 20 minutes is the temperature at 1.5 hours plus the approximate changes in temperature. So think of it kind of like the slope. So this is kind of like your y-intercept. This is always going to stay the same. So what you got in the previous answer, which was, what was it? It was your initial temperature, 77.3 degrees Fahrenheit. So how much is it going to change based on the slope you found here? So it's going to be, because your initial is 1 hour and 30 minutes, and you're trying to find 1 hour and 40 minutes, that's a 10-minute difference. And 10 minutes, and because you're finding it in hours, is going to be 10 over 60. Cross that off, you get 1/6. So it's going to be 177.3 degrees Fahrenheit plus 1/6, because remember, this is per hour, so you're trying to find only 10 minutes of that change. So 1/6 times 13.3 degrees Fahrenheit. So let's highlight this. Where did we get this? This we got from here. This we got from the rate of change at 1.5, because the problem only asked us that. Okay, and this, how did we get this? The difference between the starting, so the final minus initial. What was initial? Initial was 1.5, right? And we decided that 1.5 is equal to 130. So 1 hour 40 minus 1 hour 30, 10 minutes. But the equation is in terms of hours. So what is 10 minutes in terms of hours? 1/6 of an hour. And then you just solve, and that's what it would be. Okay, that is all that I feel that is important in this chapter. If you have any other questions, please let me know.